This is a block of cheese, and the person you see there is a person named Democritus. Democritus came up with this idea that if you took this block of cheese and cut it into pieces, and then cut those pieces into smaller pieces, and then cut those pieces into smaller pieces, eventually you would get to a piece of cheese that no matter how sharp your knife was, you couldn't cut it anymore. That piece of cheese would be so small that it would be uncuttable. And in his language, the word for uncuttable was the word atomos, which is where we get the word atom. Don't forget that red slides are where you have to take notes. You should have your notes handout ready to go. Don't forget to look for the owl and let me know where he is. And remember to fill in all of this stuff that you see here.
To the naked eye, this is just a broken-toothed gear. It's made of conventional steel composed mainly of iron and a small amount of carbon. A small quantity of carbon is enough to protect the gear from corrosion, but not enough to make it indestructible over time. To increase steel's resistance, other elements are added: nickel, manganese, chrome. This way, hundreds of different types of steel are made. As we move closer, this fracture allows us to discover the structure of the alloy. A rugged landscape materializes. Here and there, a scattering of white specks. They're tiny particles of dust. Each of these petal-shaped forms is a particle of steel called dendrite. An alloy of iron and carbon, dendrite is found in all solid matter that crystallizes in cooling. It's found in steel, aluminium, and even when cooled rapidly, steel increases in strength, a process known as tempering. Between the particles, a cavity is outlined. We'll continue our journey through this hole, which is probably due to the aging of the metal. In the background, a grain of pearl. It's easily recognized by its characteristic sliced structure. The thick black diagonal cutting through the perlite contains a little more carbon than the lighter areas around it. So do the... It's this extra carbon that gives the darker color. The fuzzy black and white flecks are faults by the microscope. At maximum enlargement, a series of tiny... Here, at last, is the atomic structure of steel. Atoms of iron and carbon regularly stacked in all directions. Beyond this, nothing more is visible for the moment.
So that little video clip that you just watched is absolutely amazing to me. I don't know if you were amazed by it, but whenever I see that video clip, I am amazed by it. I'm amazed at the fact that we can actually see actual atoms. I think this is really incredible. The atoms that you saw in that picture were about as clear of an image that we can get of atoms. What we're going to be learning about this week is the idea that we know a lot about atoms, but a lot of the things we know and a lot of the pictures that we see in the drawings that we make of atoms are something that we know from what are called indirect observations, by doing all sorts of tests to find out things about them without actually necessarily being able to see them. For example, you may already know that atoms are made out of protons, neutrons, and electrons, but you didn't see those in that picture, in that little video clip. All you could see is this sort of fuzzy outline of an atom, and that's the best we can do. Nobody's ever seen an electron. Nobody's ever seen a proton or a neutron. So how do we know that they exist? Well, we know they exist from doing tests on them, and that's what I want to talk about this week, is the tests that have been done and what we have learned about atoms over the years. Let me give you another sense, another way of thinking about how small atoms are. So this is a piece of paper. I want you to look at the piece of paper that you have, your notes paper right now. And I want you to look at the corner of that piece of paper. And I actually want you to look at the edge of the piece of paper, like the thin edge that would cut your finger if you got a paper clip. And I want you to look at that closely and look at how thin that is. Well, if you were to look at a piece of paper under a microscope, this is kind of what it would look like. And if you were to look at that little part of the paper, that little corner there, under an even more powerful microscope, this is what it would look like. Now, you probably know that paper is made out of wood. Well, these are all the little wood fibers, and this area right down here, well, that's the corner of your paper right there. So this is actually the thickness of the paper here, and that thickness is about 1 million atoms thick. So there are atoms here. This is all made of atoms, and this is about, if I'm drawing atoms here, I would have to draw 1 million atoms stacked up on top of each other in order to show you the thickness of your piece of paper. That's how small atoms are. You can fit 1 million of them stacked on top of each other, and that would only be the thickness of a single sheet of paper. So atoms are incredibly, incredibly small. As we were seeing before, they're so small that even with the most powerful tools that we have available to us right now, we can't see an atom in any real clarity. We can't see the parts that make up an atom. We can only see a really kind of fuzzy outline of an atom. So is this drawing really accurate? I mean, do we know if it's accurate? Well, I can tell you this, it's not really that accurate. This is what we would call a model of an atom. And just like a map or a globe is not an exact reproduction of the Earth. Think of a globe. Does a globe have every blade of grass on the Earth on it? Does it have every grain of sand? Does it have you on it? Does it have your house on it even? No, it doesn't have any of those things. A globe is a representation of the Earth, and it doesn't have every single detail on there exactly, but it's still useful. It's helpful. It can show us where countries are relative to each other. It can show us about how big the big countries are and how small the small countries are and how big the ocean is in comparison. It can show us where the equator and the North and South Pole are. It can really tell us a lot about the Earth, even though it's not an exact replica of the Earth. So when we look at pictures of the atom like this, I want you to think of them in the way that you think of a globe. That a globe, you know that a globe is not an exact reproduction of the Earth. Well, these pictures, like the one that you see on the screen right now, is not an exact reproduction of an atom. It's a model of an atom. And what we need to talk about here is how we can use these models and how this model, this concept of what an atom looks like, how it's changed over the years. So these pictures just represent an atom and what it kind of sort of looks like, but they're not exactly right. So what we need to do here is figure out how our concept of the atom has changed. As we've discussed, atoms are really small, and it's very, very difficult to really get a sense of what is going on inside of these things and what they look like, how they behave, what they're made out of, all sorts of things like that. Because they're so small, it's very, very difficult for us to figure out what's going on in there. And so over the years, we've come up with a lot of different ideas, and some of them have been right and some of them have been wrong. We could compare this to what we know about outer space. Outer space has the same problem in that it's very big and very far away from us, and so it's very difficult for us to learn things about it. Well, over the years, we've come up with a lot of different ideas. For a long time, people thought that the Earth was in the center of everything, and that's kind of understandable because when you look up at the sky with your naked eye, it kind of looks like everything's going around us. The stars move across the sky, the sun moves across the sky, the moon moves across the sky. Everything seems to move across the sky above us. It took us a long time to figure out that those apparent movements of things in the sky, a lot of them have to do more with the fact that we're moving, not them. The stars move across the sky, but not really because they're moving, it's because the Earth spins. Same thing with the sun. It rises and sets not because it's moving, but because we are moving. And it took us a long time to figure that out. And we understand now that the Earth is not in the center of the solar system or the center of the universe, that the Earth goes around the sun, and so do the other planets, and the moon goes around the Earth, and there's other moons that go around other planets and things like that. So we didn't know that at first, and we got it wrong at first, but we learned things along the way, and we revised and made our model of the universe and the solar system better as we went along, and we learned more and became more and more certain of what we know about things. Well, the same thing has happened to the atom. So make sure you understand that as we go through this, a lot of the ideas that I'm presenting to you now are ideas that we know are incorrect, that we have changed over time, and our ideas and our ability to understand these things have changed over time. So a lot of the things that I'm going to be telling you are incorrect, but I'm also going to be telling you the correct parts that stuck around that we now know really were the right idea. So we're going to work our way up to the real correct idea of what we now know is the atom, and that idea will probably continue to change in the future, but there are some things that we know for certain at this point. So let's start from the beginning in this guy Democritus. Well, as I said in the beginning of the video, he basically came up with this idea that if you keep cutting something into smaller and smaller pieces, you must get to a point of a smallest piece that you can never possibly cut anymore. And he said that this piece would be uncuttable, and the word in Greek for that is atomos, and that's where we get the word atom from. Now, to start things off, let's talk about what's wrong about this. Well, we now know that an atom is not uncuttable, that it's not the smallest thing that there is. In fact, we're kind of still looking for that. We haven't really found the smallest thing ever. There are certain different hypotheses and theories out there, like string theory, that gives us a kind of an idea, but we're still really not sure about what the absolute smallest things are that make up the matter in the universe. We're still working on that. But we do know that the thing that we call an atom is actually made up of smaller parts. So that's kind of not right. And it is, we can cut it into smaller pieces. So the word atom does not, although it means uncuttable in Greek, we now know that that's not really quite the best word to use. We've kept that word, but atoms are not uncuttable, but this is where the idea started. So think of this like billiard balls. They are little tiny spheres that you can't make into anything smaller. That was Democritus's concept of what we call an atom. Now, the next guy that came along is John Dalton, and we've really skipped a lot of time here. This is well over 1,000 years or a couple thousand years beyond Democritus. So it took a really long time before we really got to know things, and it took a lot of developments in technology, things like microscopes and stuff like that, in order for us to make some better assumptions here about what an atom is. So John Dalton's atomic assumptions, there are a total of 5 of them. So he started off with saying that all matter is made of atoms, and atoms are indivisible and indestructible. Indivisible. This is like in the Pledge of Allegiance, indivisible with liberty and justice for all. In case you didn't know, that word is not invisible. We are not all invisible. We are indivisible, unable to be divided. You can kind of almost see that word in there, right? Right there. Okay, so it is unable to be divided, unable to be broken down into smaller parts, and it is indestructible. You cannot destroy it. That was his first assumption. His second assumption was that all atoms of a given element are identical in mass and properties. So all atoms of gold are exactly the same. All atoms of silver are exactly the same. All atoms of oxygen are exactly the same. He said that compounds are formed by a combination of two or more different types of atoms. And he said that a chemical reaction is a rearrangement of atoms. Now, I want you to think about this for a second and think about what we know so far and which one of these things are true and which ones are false. Well, we've already talked about the fact that matter is in fact made of atoms, but atoms are not indivisible and they're not indestructible. You can break apart atoms into smaller pieces, so this is not correct, especially this part here, that second sentence here. This is not right. No. Bad Dalton. Wrong on that one. Not a bad try, but he was wrong. All of these other ones, these guys are good to go. As far as we know, this pretty much describes matter, and these are all correct. All right, our next guy, J.J. Thomson. He discovered that atoms have a charge, a plus and minus charge. We've talked a lot about this. Remember when we talked about electricity, we talked about atoms having positive and negative charges. J.J. Thomson is the guy that figured this out, and he figured it out in a very interesting way using a gadget like this, which to me looks kind of like a laser beam from some old sci-fi movie or something like that. And honestly, that's basically what it is. It's not a laser beam, but it's a beam of charged particles, and these charged particles did something very interesting. This is what's called a cathode ray tube, or a CRT. And cathode ray tubes put out a stream of atoms that were attracted and repelled by charged plates, basically magnets. And he was able to make this beam bend. Now, this has a very interesting outcome to it, and this is that these were eventually used in televisions because they were able to take little charged particles and bend them to wherever they wanted to go on the screen, and those little charged particles would tell which pixels to light up on the screen. So this became a very useful invention, but originally it was something that was used to understand how an atom works, and you can see this in this video clip. So J.J. Thomson hypothesized that atoms were composed of thousands of negative electrons in a cloud of positive energy, and he had a name for this. He called it the plum pudding model. Now, plum pudding is a very common, popular treat in England. If he was in the United States, he might have called it the blueberry muffin model, or maybe the chocolate chip cookie model. However you want to think about it, it's basically a bunch of positive stuff with little chunks of negative stuff stuck in there, kind of like the blueberries in a blueberry muffin or the chocolate chips in a chocolate chip cookie. All right, the next guy is Ernest Rutherford, and Ernest Rutherford really built off of what J.J. Thomson started. Ernest Rutherford took the concepts that J.J. Thomson introduced, and he kind of went with them, and he decided to do some extra experiments with these, and he found out something very interesting. Now, the experiment he did was called the gold foil experiment. The gold foil experiment kind of went something like this. The assumption was that here is the plum pudding model put forth by J.J. Thomson, and the plum pudding model basically was a big fluff ball. And the reason why it was a big fluff ball is because it was all of these charges were kind of very spread out in this. So what he figured was that if you shot some charged particles through it, they basically should go right through it. And they shouldn't be very affected because this is a very kind of soft material that allows charged particles to go right through it because the charges aren't very concentrated. They're very spread out in this. So he figured that something like this should happen. If you shot some charged particles, they should just kind of go right through. So he did this thing called a gold foil experiment, and right in the middle of this you have some gold foil here, down here, and that gold foil, if you've ever seen gold leaf that's on the edges of books, gold leaf is something that is basically a very, very thin little film of gold. You can stretch gold out and make it into a very, very thin sheet. And this was important because that means it could only be like a few atoms or maybe 100 atoms thick. Remember, the thickness of your piece of paper is 1,000,000 atoms thick. So this is really, really thin sheet of gold here. And that was good because he thought that if you could send some charged particles through this thin sheet of gold, that they should basically just go right through it and be unaffected. So what he did was, this is the little thing that shoots out the charged particles, and they go through the gold foil here. And the idea is this thing here is a screen that will detect where these charged particles hit. And they literally would turn off the lights in the room and do this, and you could see little lights on this screen. Every time a charged particle hit the screen, it would light up the screen a little bit, and they could see this as long as they sat in the room long enough and let their eyes adjust. They could actually see these little glowing dots on the screen. And so the idea again was that all these would just kind of go straight through. And so, you know, it's like a little puffball and they go right through it, right? No problem. But the big surprise here was that some of them didn't go straight through. And I want to be very clear about this. The hypothesis was that all of them would go straight through. The actual experimental result was that most of them did go straight through. That's an important part to remember. Most of the particles did go right through and they were unaffected. It's these few extra ones that bounced off and went over that way, or went over that way, or some of them even came straight back. This was extremely surprising, and this made Ernest Rutherford kind of think twice about this. So, the gold foil experiment, some positive particles were deflected when shot through a thin sheet of gold foil, and it's very important to remember that it was only a few of them, okay? This brought about a very famous quote by Ernest Rutherford. He said it was almost as incredible as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back to hit you. This was very surprising to him. He did not expect this at all. And so he came to the conclusion that it was really not a big puffball, that there were charges in this atom, but they were arranged in a different way, more like this. They were more concentrated, with the positive parts being all concentrated in this very dense center that he called the nucleus, and that the negative charges were all flying around. And a big part of this was the fact that the space in between here was exactly that. It was empty space, that most of the atom was actually empty space. And in fact, this is nowhere near being accurate, this picture here, as far as the amount of empty space. So atoms must be mostly empty space with a small, dense, positive nucleus. Now I want you to try to picture this. That picture that I showed you, like I said, was not very accurate. Picture it like this. What's more accurate is if you were in a big football stadium and you put a marble in the center of the stadium, the electrons would be flying around out where the stands are. That's how much empty space there is. Now, I want to be clear about this. I am using this as a model, so this is a very much blown up, enlarged version of the atom. The atoms are actually really much smaller. But if we blew up the nucleus of the atom to the size of a marble, the electrons would be way out here in the stands. In other words, there is a whole lot of empty space, at least in the kind of on the size scale of the atom. There's a lot of empty space here. Most of the atom is made up of empty space. Let's think about this for a second. You're made of atoms. That means you are mostly empty space. The vast majority of the thing that you call your body is nothingness. It's empty space in between the atom's nucleus and the electrons. All right, so the next guy is going to build on this idea some more. Niels Bohr kind of had this issue with the idea that the center of the atom was positive and the electrons going around the outside were negative. Well, why did he have a problem with this? Well, think about this. These electrons should be attracted to the center and they should kind of fall into it. So he basically came up with this idea that solved that problem, and he said that electrons orbit on specific levels or shells. Now, this is a little complicated about why this solves the problem, but basically the idea is that as long as they are flying around here in certain specific areas, that their speed going around here will kind of counteract the fact that they're being pulled in towards the center. It's kind of the same reason why we don't fall into the sun. So the electrons can jump from one shell to another when they absorb or release energy. They can't be really in between the shells, though. They can only be on these shells, and these shells become very, very important. Please, please remember this part. This is extremely important. These energy shells and the electrons that are in them are the whole basis of the entire subject of science that we call chemistry. We're going to learn a lot more about that, but get that soaked into your head, that this is the model that we will continue to use. I'm about to show you that this is actually not really that accurate as far as how atoms really look, but it's a very good and very useful model in the same way, like I said before, that a globe is a useful model, even though it's not exactly the same as the Earth. It's very useful. And so this Bohr model, named after Niels Bohr, not because it's boring, this Bohr model is the model that we will be using from now on. So make sure you understand this. So label the nucleus, label the electrons, and label the shells in your notes, please. Nucleus, electrons, and shells. All right, so this is the actual current model of an atom, and it is called the electron cloud model. This model is complicated. This is a tough one because it gets us into something called quantum mechanics or quantum physics. Quantum physics is a way of explaining how the universe works. And it's something that is very, very well understood by scientists and really accurately describes the way the universe works. But unfortunately, it kind of goes against our experiences of the universe. So I'll give you an example of what I mean, and this may sound familiar from when we were talking about light. Our experience of the universe is that things are in a place at a certain time. And you can be here or you can be there, but you can't be both. And you are definitely somewhere. Those things all seem like very obvious statements. Unfortunately, though, in quantum physics, and that means on the level of very, very small things like atoms and electrons and stuff like that, those things that I just said are not true. Things are not in a place. Things are partially in one place and partially in another place. And I do not mean that they are broken up into pieces and one piece is in one place and one piece is in another place. I mean like an individual thing is not in one place at one time. It's just sort of in one place. This is the way that electrons really work. So the electron cloud model basically says that these are the areas where the electrons will most likely be found. This is about probability. So the electrons will probably be there, but they won't actually be there. They don't have to be there. They could be in other places. It's just where these dots are the more likely places that they could be. They could be here. They could be here. They could be on Mars. It's just not very likely that they would be in there, in those places. Now, it's somewhat likely that they might be here. It's extremely ridiculously unlikely that they would be on Mars, but it's not impossible. It's a very weird kind of thing here and very tough to figure out and very tough to understand. So just trust me on this one when I say that we are very confident that this is how things are. It's just a little bit tricky. So we can't figure out exactly where they are. It's just kind of they're in certain places. And those shells that I was talking about in the Bohr model, yeah, they don't really look like circles exactly. They look like these shapes. Each shell kind of, these are, when I talk about the idea of where the electrons will probably be, these are kind of maps of that, of where they will most likely be depending on which shell they're in. And so it's kind of complicated. And this is, even though this still isn't really a picture of an atom, this is more like what atoms look like than those circles and dots that we use. But like I said, the one that we're going to use most often is the Bohr model because that's simple and it allows us to understand what's going on in the atom. Just like a globe is a simplified version of the actual world, but it's okay because it helps us get from one place to another. All right, so are you still with me? Hopefully I didn't hurt your brain too much talking about quantum physics and all that kind of stuff. I know it's a rather complicated and kind of hard to understand subject, but fortunately for you in 8th grade, you don't really have to have a very good understanding of quantum physics. But I would really encourage you, if you find that interesting in any way, to go onto YouTube and look up some videos about that. And I'll try to include some within this, this homework. So what you do need to know is that Democritus started this whole thing out by talking about the smallest piece of something being uncuttable, and he called that atomos. Dalton kind of used that idea and continued on with it and basically added our concepts of chemistry to this. The idea that atoms stick together and in chemical bonds, and the idea that compounds are just groups of atoms, and that we have these things called elements on the periodic table and stuff like that. Thomson then further went with that, and he's the first guy to say that atoms are not the smallest part, that there are parts that make up atoms, and he's the one that kind of started talking about this idea of electrons and protons and things like that, and different things within that atom. So he said that atoms have charges, positive and negative, and he used the cathode ray tube, or the CRT, to explain that and to figure that out, and he called his model the plum pudding model. Rutherford piggybacked on the idea of the plum pudding model and talked about the idea that these positive and negative charges were actually in specific places within the atom. That the positive charges were in the nucleus, and that nucleus was very small and dense, and that the negative charges were flying around the nucleus, and there was a lot of empty space in between. And he used the gold foil experiment to prove that. Bohr then took that concept, that vision of the atom, and added shells in order to get rid of this problem of the electrons being pulled into the positive nucleus. And our most recent and most confusing one is the electron cloud model, and we will learn all about that this week, and I will see you then.